In 1977, two spacecraft left Earth on a mission to visit the giant planets. They did. They sent back some of the most iconic images in human history. And then, as far as most people know, the story ended. It did not. After the last planet disappeared behind them, the Voyager probes entered a part of space no instrument had ever touched. And what they found there was not emptiness. It was a boundary, a threshold between everything the sun controls and everything it does not. A region so strange that it forced scientists to redraw the edge of the solar system itself. The greatest chapter of the Voyager mission is the one almost nobody talks about. Tonight, we tell it. If this is the kind of deep science storytelling you want more of, hit like and subscribe. It genuinely helps this channel keep going and keeps these stories coming your way. Are you comfortable? Now, let's begin. In the summer of 1977, two spacecraft launched from Cape Canaveral roughly 16 days apart. They were not the largest machines NASA had ever built. They were not the most expensive. Each one weighed roughly 1,800 pounds, about the mass of a small car. They carried cameras, magnetometers, plasma detectors, cosmic ray sensors, and a handful of other instruments designed to survive deep space long enough to photograph 2, maybe 3, maybe 4 planets before the radiation and the cold and the distance killed them. Their power supply was a set of 3 radioisotope thermoelectric generators strapped to a boom, converting the heat of decaying plutonium into electricity. At launch, each spacecraft generated roughly 470 watts, enough to run a few household light bulbs. That was the entire energy budget for everything: heating, computing, transmitting, and every science instrument aboard. The mission was called Voyager, and it was born from an accident of gravity. In the late 1960s, a young aerospace engineer at the Jet Propulsion Laboratory named Gary Flandreau was studying trajectories for missions to the outer solar system. He discovered something that most people in the field had not yet realized. In the late 1970s, Jupiter, Saturn, Uranus, and Neptune would align on the same side of the Sun in a geometric configuration that occurs roughly once every 175 years. That alignment meant a spacecraft launched at the right moment could use the gravity of each planet to sling itself toward the next one, gaining speed without burning fuel, hopping from world to world like a stone skipping across water. The concept was called the Grand Tour. It was elegant. It was cheap, relatively speaking, and the window was closing. Miss the late 1970s and humanity would have to wait until the 22nd century for another chance. NASA originally planned a more ambitious set of missions under the Grand Tour name, but budget cuts in the early 1970s scaled the program back to 2 spacecraft aimed primarily at Jupiter and Saturn. The extended visits to Uranus and Neptune were technically possible, but not guaranteed. They depended on everything going right: the spacecraft surviving, the instruments lasting, the funding continuing. Nothing about space exploration works that cleanly, and yet, almost impossibly, it did. Voyager 2 launched first on August 20th, 1977. Voyager 1 launched 16 days later on September 5th. Despite launching second, Voyager 1 traveled a faster trajectory. It would reach Jupiter first, pass Saturn first, and ultimately fly farther and faster than its twin. But Voyager 2 carried the more versatile flight path. If all went well, it could visit all 4 giant worlds. Voyager 1 could not. A decision made at Saturn would guarantee that. The first destination was Jupiter. Voyager 1 arrived in March of 1979. Voyager 2 followed in July, and what the cameras sent back rewrote the textbooks on planetary science overnight. Jupiter was not the quiet gas giant people imagined. Its atmosphere was a boiling chaos of storms, jet streams, and cyclonic vortices. The Great Red Spot, which astronomers had observed through telescopes for centuries, turned out to be a storm larger than Earth, with wind speeds exceeding 400 miles per hour. But the planet itself was almost secondary. The moons were the revelation. Io, the innermost of Jupiter's 4 large moons, was supposed to be a dead, cratered rock. Instead, Voyager 1's cameras caught something no one had predicted: active volcanoes. Plumes of sulfur and sulfur dioxide erupting hundreds of miles above the surface, painting the moon in shades of orange, red, and yellow. Io was the most volcanically active body in the entire solar system. Not Mars, not Venus. A moon smaller than Earth's own, being squeezed and heated by the tidal forces of Jupiter's gravity until its interior churned and erupted constantly. No model had predicted it. Navigation engineer Linda Morabito spotted the first volcanic plume in a navigation image. She was not even looking for volcanoes. Nobody was. Europa, the next moon out, showed something equally startling in a completely different direction. Its surface was almost perfectly smooth. No large craters. Instead, it was covered in a web of crisscrossing cracks and ridges, like a shattered eggshell that had been carefully reassembled. The best explanation was that beneath that icy crust, Europa harbored a liquid ocean. An ocean of salt water, kept warm by the same tidal forces that tortured Io, hidden under miles of ice. The implications for the possibility of life beyond Earth were staggering, and they emerged not from a planet but from a moon that most people at the time could not have named. Ganymede and Callisto each revealed their own surprises. Ganymede showed a surface of grooved terrain suggesting tectonic activity. Callisto was ancient and heavily cratered, a frozen record of bombardment stretching back billions of years. Between them, Jupiter's moons presented a miniature solar system's their own, each world distinct, each with its own story. The 2 spacecraft then continued to Saturn. Voyager 1 arrived in November of 1980. Voyager 2 followed in August of 1981. Saturn's rings were not the simple, solid sheets they appeared to be from Earth. Voyager revealed them as thousands of individual ringlets, braided and sculpted by the gravity of tiny shepherd moons embedded within them. Gaps that telescopes had shown as clean separations turned out to be filled with finer structure, waves and density patterns rippling through the ring material like grooves on a vinyl record. The rings were a laboratory for orbital dynamics, and they were far more complex and beautiful than anyone had predicted. But the decision that shaped the rest of the Voyager story happened at Titan. Saturn's largest moon was shrouded in a thick orange haze of nitrogen and methane, an atmosphere denser than Earth's own. Scientists were desperate to study it. Titan was, and still is, the only moon in the solar system with a substantial atmosphere. The chemistry happening in that haze bore similarities to what scientists believed existed on early Earth before life emerged. To get a close look at Titan, mission planners aimed Voyager 1 on a trajectory that passed roughly 2,500 miles above the moon's cloud tops. The flyby was a success. The instruments detected nitrogen as the dominant atmospheric gas, measured surface pressure at roughly 1.5 times Earth's sea level, and identified complex organic molecules in the upper atmosphere. Titan became one of the most intriguing worlds in the solar system, a place where chemistry was doing something that looked like a prelude to biology. But that trajectory came at a cost. The close Titan flyby bent Voyager 1's path sharply upward, out of the plane where the planets orbit. After Saturn, Voyager 1 could not visit Uranus. It could not visit Neptune. It was heading up and away from the planetary disk, aimed at nothing in particular, moving at roughly 38,000 miles per hour toward the outer edge of the solar system. The planetary mission for Voyager 1 was over. Voyager 2 carried the Grand Tour forward alone. In January of 1986, Voyager 2 reached Uranus. It was the first, and as of today, the only spacecraft ever to visit this world. The planet was strange, tilted almost completely on its side, rolling along its orbit like a ball rather than spinning upright like its neighbors. Its atmosphere appeared nearly featureless in visible light, a pale blue-green globe with almost no cloud detail. Beneath that calm exterior, instruments detected fierce winds and a magnetic field tilted 60 degrees from the planet's rotation axis, offset from the center as if someone had installed it crooked. The moons were the surprise again. Miranda, the smallest of Uranus's 5 major moons, looked like it had been smashed apart and reassembled. Its surface was a patchwork of wildly different terrains, deep canyons, ridged plains, and a cliff face later measured at roughly 12 miles high, one of the tallest known drops in the solar system. The geology made no obvious sense. It still does not entirely. 3.5 years later, in August of 1989, Voyager 2 arrived at Neptune. The encounter was 12 years and roughly 4.5 billion miles from launch. The spacecraft was operating on instruments designed in the early 1970s, running on a computer with roughly 69 kilobytes of usable memory. The cameras needed long exposure times because Neptune receives so little sunlight, and the spacecraft's own motion would blur the images. Engineers at the Jet Propulsion Laboratory solved this by programming the spacecraft to slowly rotate during each photograph, compensating for its movement with mechanical precision that rivaled anything on Earth. The technique worked. Neptune was not the featureless world some expected. It had a great dark spot, a massive storm system visible in the southern hemisphere, with the fastest winds ever measured on any planet exceeding 1,200 miles per hour. It had clouds of methane ice casting shadows on the deeper atmosphere below. It had a system of faint rings, confirming what ground-based observations had tentatively suggested. And Triton, Neptune's largest moon, was the final gift. A world captured from the outer solar system, orbiting backward compared to everything else around Neptune. Its surface was young. Nitrogen ice geysers were erupting from beneath the surface, shooting dark plumes 5 miles high into the thin atmosphere. The terrain was unlike anything the mission had seen before. Frozen lakes of nitrogen, cantaloupe-textured plains, a world resurfacing itself through cryogenic volcanism at temperatures of roughly minus 390 degrees Fahrenheit. It was extraordinary, and it felt like an ending. After Neptune, there were no more planets to visit. The Grand Tour was complete. Voyager 2, like its twin before it, was now heading outward with no destination ahead that anyone could name on a classroom poster. The public narrative of the Voyager mission had built steadily for 12 years. From Jupiter's storms, to Saturn's rings, to the strangeness of Uranus, to Neptune's dark winds. Each encounter was a crescendo, and Triton was the final note. Then came the image that sealed the story shut. On February 14th, 1990, as Voyager 1 was approximately 3.7 billion miles from the Sun, the cameras were turned around. The instruction came at the urging of Carl Sagan, who had been part of the Voyager imaging team from the beginning. He wanted the spacecraft to take one last photograph, not of a planet up close, not of a moon or a ring or a storm. He wanted Voyager 1 to look back toward the inner solar system and photograph Earth. The image that arrived was haunting. Earth appeared as a tiny point of light, less than a single pixel across, suspended in a beam of scattered sunlight, a pale blue dot in the vastness of space. Sagan wrote about it later in words that became some of the most quoted in the history of science. He described that dot as everything humanity had ever known. Every war, every love story, every invention, every civilization, all of it on a mote of dust hanging in a sunbeam. The pale blue dot became one of the most famous photographs ever taken. And for most people, it became the emotional conclusion of the Voyager mission. The probes had visited the planets. They had shown us our world from the outside. The cameras were switched off to save power. The story was over. Except it was not. In that same season, something else happened that almost nobody outside the space science community noticed. The Voyager program was formally redesignated. Its new name was the Voyager Interstellar mission. The abbreviation was VIM. The goal was no longer planetary science. It was something entirely different. The probes were now tasked with detecting and studying the outer boundary of the sun's influence, the place where the solar wind, the stream of charged particles constantly blowing outward from the sun, finally meets the gas and plasma that fills the space between the stars. No one had ever been there. No instrument had ever measured it directly. The theoretical models said this boundary existed somewhere between 50 and 150 astronomical units from the Sun. 1 astronomical unit is the distance from Earth to the Sun, roughly 93 million miles. The boundary was, at minimum, billions of miles ahead of both probes. The models disagreed on where exactly it was. They disagreed on what it would look like. They disagreed on how the transition would happen. And they disagreed on what lay beyond. The Voyager Interstellar mission was, in essence, a bet. A bet that these two spacecraft, built to survive 4 years, carrying instruments designed in the Nixon administration, running on slowly decaying plutonium, could last long enough to reach a boundary that might be decades of travel time away. And that, if they reached it, they could still detect what was there and send the data home across a distance so vast that the radio signal, traveling at the speed of light, would take more than a day to arrive. The scientific community understood the significance. The public, largely, did not. In the years following the Neptune flyby, Voyager faded from the headlines. The Hubble Space Telescope launched in 1990. The Galileo mission went to Jupiter. Cassini went to Saturn. Mars rovers captured the public imagination. Each new mission offered the thing that makes space exploration viscerally exciting to most people: a destination. A world with a surface, an atmosphere, a story you could tell over dinner. Voyager had no destination. It was heading into a region with no name that most people had never heard of. The heliosphere, the termination shock, the heliopause. These terms were not in the public vocabulary. They were not in most science textbooks below the graduate level. The space the probes were crossing was not empty, but it contained nothing a camera could photograph. Nothing you could put on a poster. The instruments still operating were measuring magnetic fields, charged particles, plasma waves, and cosmic rays. Data streams of numbers, not images. The kind of science that fills journals, not front pages, and so a story took hold that persists to this day. The story that Voyager's great achievement was the Grand Tour, that the mission peaked at Saturn's rings and Neptune's winds and the pale blue dot, that everything after was an epilogue, a slow, quiet fade into the void. Two aging spacecraft drifting in silence, carrying golden records that no one would ever play, heading towards stars they would never reach. That story is wrong. It is wrong not because the Grand Tour was unimportant. The planetary encounters were magnificent. They rewrote our understanding of the outer solar system, and they deserved every headline they received. But the story is wrong because it treats the planets as the point, and the planets were not the point. The planets were the beginning. What lay ahead of both probes after 1989 was not emptiness. It was the edge of the solar system itself. Not the theoretical edge drawn on a diagram, not a textbook abstraction. A physical, measurable boundary where the influence of the sun ends and the influence of the galaxy begins. A region that no probe had ever reached, that no instrument had ever sampled, and that the best models of the era could only approximate. The probes were heading toward a place where the solar wind, which had been pushing outward past every planet at over 1 million miles per hour, would finally slow down, then stop, then give way to something else entirely. The interstellar medium, the gas and dust and magnetic fields and plasma that fill the space between the stars. Material ejected by the deaths of giant suns millions of years ago. The stuff that the solar system is embedded in, like a ship moving through an ocean that no one aboard has ever tasted. The probes were not coasting into irrelevance. They were approaching the most important measurement they would ever make, the first direct contact with the boundary between inside and outside, between the sun's domain and everything beyond it. But that measurement was decades away, and in the meantime, both spacecraft had to survive. Every year after the Neptune encounter, the power output from the radioisotope thermoelectric generators dropped by roughly 4 watts. 4 watts per year, compounding, permanent. The plutonium was decaying. The thermocouples that converted its heat into electricity were degrading. The total power available to each spacecraft was falling steadily, and every watt lost was a watt that could not be recovered. Engineers at the Jet Propulsion Laboratory began making choices that no one had planned for during the original mission design. Which heaters to turn off, which instruments to shut down, how to balance the need to keep fuel lines from freezing against the need to keep science instruments running against the need to keep the transmitter powered, so that the data could reach Earth at all. The spacecraft were designed for a 4-year mission. By 1990, they were 13 years old. By 2000, 23 years old. Every additional year was borrowed time. Every instrument that kept functioning was a small miracle of engineering and luck. And every watt of power saved by shutting something down was a watt that might keep the spacecraft alive long enough to reach the boundary that the entire Voyager interstellar mission existed to find. The distances were already staggering. By the mid-1990s, Voyager 1 was more than 50 astronomical units from the Sun. Voyager 2 was past 40. A command sent from Earth to either spacecraft traveled at the speed of light and still took hours to arrive. If something went wrong, the round-trip communication time meant that engineers would not know about it for the better part of a day. And by the time they could respond, another day would pass before the fix arrived. Operating a spacecraft under those conditions is not the same as controlling a Mars rover with a 20-minute delay. It is a different category of patience entirely. During those years, the probes were not idle. They were measuring. The cosmic ray detectors counted the energetic particles arriving from deep space. The magnetometers track the sun's magnetic field as it stretched and spiraled outward. The plasma wave instruments listened for oscillations in the charged particles surrounding the spacecraft. The data was quiet. The readings were gradual. There were no volcanic plumes or ring shadows or geysers. But the instruments were watching the solar wind thin. They were recording the slow, steady change in the environment as the probes moved farther from the sun than any human-made object had ever traveled. And somewhere ahead, invisible and unmapped, the boundary was waiting. The models said the termination shock, the first major feature of the solar system's outer edge, lay somewhere around 80 to 100 astronomical units from the sun. At that distance, the solar wind, which blows outward supersonically for billions of miles, would abruptly slow to subsonic speed, piling up against the pressure of the interstellar medium outside. It would be like a river hitting a wall of thicker fluid, a transition from fast and thin to slow and dense and hot. The physics predicted it, the math demanded it, but no instrument had ever been there to check. The probes were getting closer. Every day, every year, they moved farther from the sun and closer to the shock. The data streams continued. The power continued to drop. Instruments continued to be shut down one by one, sacrificed to keep the remaining ones alive a little longer. And the question that drove the entire Voyager interstellar mission hung in the silence between transmissions. Would the spacecraft survive long enough to reach the edge? What happened next would take a generation of patience to unfold. And when the first boundary finally appeared in the data, it was not where anyone expected. It was not shaped the way anyone predicted. And it revealed that the solar system's edge is not a clean line at all. It is something far stranger and far more alive than any model had imagined. For 15 years, almost nothing happened. That sentence sounds like a criticism. It is the opposite. Between the Neptune encounter in 1989 and the first boundary crossing in 2004, the two Voyager spacecraft traveled billions of additional miles through a region of space that had no name the public recognized, no feature visible to a camera, and no event dramatic enough to break through the noise of daily news. The probes sent data. Engineers monitored systems. Scientists published papers on gradual trends in the cosmic ray counts and magnetic field measurements. And the world largely forgot they were still out there. That forgetting is understandable. The rhythm of public attention in space exploration is tuned to arrivals. A spacecraft reaches Mars and the cameras show red dirt and everyone pays attention. A probe drops into the atmosphere of Titan and people lean forward. Voyager had nothing to arrive at. No surface to land on, no cloud to descend through. It was crossing a void that most people imagined as simple emptiness. The black space between here and the stars, featureless and flat and cold. It was none of those things. But understanding why requires understanding what the probes were actually measuring during those quiet years. The sun does not simply sit in space and shine, it exhales. Constantly, in every direction, at all times, the sun releases a stream of charged particles, mostly protons and electrons, moving outward at speeds between roughly 200 and 500 miles per second. This stream is the solar wind. It is not a metaphor. It's a physical flow of material, a plasma, and it fills the entire solar system. Every planet orbits inside this wind. Every moon, every asteroid, every comet that comes close enough to develop a tail does so because the solar wind is pushing material away from its surface. The wind is invisible to the eye, but it is as real as the air moving past your face on a breezy afternoon. As the solar wind moves outward from the sun, it does not maintain its full strength forever. It spreads, it thins. The density drops with the square of the distance. By the time it reaches the orbit of Neptune, roughly 30 astronomical units from the sun, the wind is a whisper compared to what it was at Earth's orbit. But it is still supersonic. It is still moving faster than the speed at which pressure waves can propagate through it, which means information about what lies ahead cannot travel upstream. The wind does not know what it is about to hit, but something is out there. The interstellar medium, the gas and plasma and dust that fills the space between stars in our galaxy, exerts its own pressure. It pushes back, and somewhere far from the sun, the outward force of the solar wind and the inward pressure of the interstellar medium reach a balance. The wind, which has been blowing supersonically for billions of miles, can no longer maintain that speed. It slows, abruptly, violently. The transition from supersonic to subsonic flow creates a shockwave, a standing wall of compressed and heated plasma that wraps around the entire solar system. This is the termination shock. And in the years between the Neptune flyby and the early 2000s, both Voyager probes were approaching it. They were approaching it at different speeds, along different trajectories, through different regions of the solar wind. Voyager 1 was heading roughly northward relative to the plane of the planets, climbing away from the solar system at approximately 38,000 miles per hour. Voyager 2 was heading roughly southward, and in a different direction entirely, slower by a few thousand miles per hour, but covering its own path through a different slice of the heliosphere. This separation was not a flaw in the mission design. It was one of its greatest accidental gifts. Two probes crossing the same boundary in different places at different times would reveal whether that boundary was symmetric or whether it varied depending on where you punched through. During the long cruise, the instruments that mattered most were not the cameras. The cameras had been switched off after the pale blue dot. The instruments that mattered were the ones that could feel the environment without seeing it. The magnetometer, carried on a long boom to keep it away from the spacecraft's own magnetic signature, measured the direction and strength of the magnetic field. The cosmic ray subsystem counted energetic particles arriving from outside the solar system. Galactic cosmic rays that had been deflected and partially blocked by the solar wind. The low-energy charged particles instrument measured ions and electrons at lower energies, including those produced by the interaction of the solar wind with the interstellar gas leaking into the heliosphere. And the plasma wave subsystem, with its two long antennas extending roughly 30 feet behind each spacecraft, listened for oscillations in the surrounding plasma, vibrations that could reveal the density and behavior of the charged material through which the probes were flying. Each of these instruments drew power. Each one competed for a share of the slowly shrinking electrical budget, and each one, in the years ahead, would prove essential. The first hints that the termination shock was approaching came not from a single dramatic reading, but from a slow accumulation of subtle changes. Through the late 1990s and into the early 2000s, the cosmic ray counts on both spacecraft began to rise. Galactic cosmic rays, the high-energy particles that originate from supernova explosions and other violent events far beyond the solar system, are normally deflected by the solar wind. The stronger the wind, the fewer cosmic rays penetrate to the inner solar system. As the probes moved farther from the sun and the wind around them weakened, more of these galactic particles were reaching the detectors. The counts ticked upward year after year. At the same time, the magnetic field measurements showed the solar magnetic field becoming increasingly disordered. Closer to the sun, the field follows a relatively clean spiral pattern, wound by the sun's rotation the way water from a spinning sprinkler traces an arc across a lawn. Farther out, that spiral grew increasingly tangled. Irregularities accumulated. The field was beginning to feel the back pressure of the interstellar medium pushing against it from outside. Then, in late 2003, something unexpected happened aboard Voyager 1. The readings from two of its particle instruments changed sharply. The flux of lower energy particles surged. Higher energy particle counts shifted. The magnetic field intensity increased. It looked, to some researchers, like the spacecraft had just crossed the termination shock. Papers were published arguing that the crossing had occurred. Other scientists disagreed. The debate was heated and technical and unresolved for months. The problem was that the plasma science instrument on Voyager 1 had stopped working back in 1980 during the Saturn encounter. Without it, there was no direct measurement of the plasma density and speed around the spacecraft. The team could infer what was happening from the particle and field data, but they could not confirm it with the one instrument that would have settled the question immediately. The answer came in December of 2004. Voyager 1, now roughly 94 astronomical units from the Sun, registered a set of changes across its remaining instruments that left little room for argument. The magnetic field strength jumped. The intensity of lower energy particles increased sharply and stayed elevated. The character of the plasma environment had fundamentally changed. Voyager 1 had crossed the termination shock. The solar system had an edge, and a human-made object had just touched it. But the data did not match the textbooks. Not exactly, not cleanly, not in several important respects. The models had predicted that the termination shock would be a relatively stable structure, a well-defined boundary sitting at a roughly consistent distance from the Sun in all directions. The reality was different. The shock was dynamic. It moved. It responded to changes in the solar wind caused by the 11-year solar activity cycle. When the Sun was active and the wind blew harder, the shock was pushed outward. When the Sun quieted and the wind weakened, the shock contracted inward. Voyager 1 appeared to have crossed it during a period when the shock was relatively close, drawn inward by a quiet phase of solar output. The second surprise was what happened to the solar wind at the shock. Models predicted that when the wind slowed from supersonic to subsonic speed, most of its kinetic energy would be converted into thermal energy, heating the solar wind plasma. The ions in the wind should have become much hotter on the downstream side of the shock. What the instruments found was that the thermal solar wind ions were heated far less than expected. The energy had gone somewhere else. It had been transferred primarily to a population of particles called pickup ions. Pickup ions are interstellar atoms, mostly hydrogen, that drift into the heliosphere from outside and get ionized by the solar ultraviolet radiation or by charge exchange with solar wind protons. Once ionized, they are picked up by the solar wind's magnetic field and carried along. They are heavier and more energetic than typical solar wind particles. And at the termination shock, these interstellar immigrants absorb the lion's share of the energy. The shock was not heating the solar wind the way anyone expected. It was energizing the interstellar material that had infiltrated the solar system from outside. This was a fundamental surprise. It meant that the boundary between the solar system and the interstellar medium was not a clean separation. It was a zone of mixing. Interstellar material was already inside the boundary, already interacting with the solar wind, and at the shock itself, that material was being preferentially energized. The edge of the solar system was not a wall, it was a membrane, and material from outside was passing through it. The third surprise concerned anomalous cosmic rays. These are a specific category of particle that scientists have been studying for decades. They are interstellar atoms that enter the heliosphere, get ionized, picked up by the solar wind, carried out to the termination shock, and then accelerated to very high energies at the shock itself. At least, that was the theory. The termination shock was supposed to be the accelerator that produced anomalous cosmic rays. It was one of the central predictions of heliospheric physics. Voyager 1 crossed the shock. The anomalous cosmic rays were present, but they were not being accelerated at the location where Voyager 1 crossed. The particle energy spectra did not show the signature of local acceleration. Either the shock was accelerating these particles somewhere else, perhaps at a different latitude or a different face of the shock that Voyager 1 did not cross, or the mechanism was more complicated than the models assumed. Either way, a cornerstone prediction about the termination shock had failed at the one point in space where it was tested. This is the nature of boundary science. You go to the boundary expecting a confirmation. You get revision instead. 3 years later, Voyager 2 provided the comparison. In August of 2007, roughly 84 astronomical units from the Sun, Voyager 2 crossed the termination shock, 10 astronomical units closer to the Sun than its twin. The difference was enormous. It meant the termination shock was not a sphere. It was lopsided, pushed inward on the side where Voyager 2 crossed and pushed outward on the side where Voyager 1 had crossed. The asymmetry was driven partly by the direction the solar system is moving through the interstellar medium, which compresses the heliosphere on the leading side, and partly by the orientation of the interstellar magnetic field pressing against the boundary from outside. Voyager 2's crossing was scientifically richer in one crucial way. Its plasma science instrument still worked. On Voyager 2, it had kept running. It was still operational after nearly 3 decades, and at the termination shock, it provided the first direct measurement of the plasma conditions on both sides of the boundary. The solar wind speed upstream of the shock, the density change across it, the temperature on the downstream side. Data that Voyager 1 could only infer, Voyager 2 measured directly. The plasma science instrument confirmed what the particle data had suggested. The shock was real. The solar wind slowed from supersonic to subsonic. The plasma compressed and heated, though again not as much as models predicted for the thermal ions. And the environment downstream of the shock, the region scientists call the heliosheath, was turbulent, dynamic, and thoroughly unlike the smooth, gradually declining solar wind that the probes have been flying through for 28 years. The heliosheath is the region between the termination shock and the heliopause, the outer boundary where the solar wind finally stops and the interstellar medium begins. Before Voyager, it was imagined as a relatively calm transition zone. The solar wind, now subsonic, would gradually slow, further turn, and flow along the inside of the heliopause like water flowing along the inside of a container. The flow would be orderly. The field would be smooth. The transition would be gradual. None of that was accurate. What Voyager 1 found as it moved through the heliosheath was chaos. The magnetic field was not smooth. It was tangled into structures that researchers eventually described as magnetic bubbles, regions roughly 1 astronomical unit across, where the field had folded back on itself, creating isolated magnetic islands. The heliosheath was not a calm river. It was froth, a turbulent, foaming layer of magnetic complexity that no model had anticipated. To understand why this matters, consider what the smooth model implied. If the heliosheath were an orderly region, it would mean the solar system's outer boundary acts as a simple shield, a predictable layer that deflects galactic cosmic rays in a steady, calculable way. Models of how much radiation reaches the inner planets were built on that assumption. A smooth sheath means predictable shielding. A frothy, bubbling sheath means something different entirely. The magnetic bubbles create a maze. Cosmic rays entering the heliosheath from outside do not encounter a uniform barrier. They encounter a labyrinth of magnetic islands, some deflecting them, some trapping them temporarily, some channeling them inward along paths that a smooth field model would never predict. The shielding is still real, but it is erratic, variable, and far harder to model than anyone had assumed. Voyager did not just discover that the heliosheath was turbulent. It discovered that the solar system's radiation shield operates by a mechanism that the textbooks had not described. In 2011, computer simulations run by Mehrav O.H. at Boston University and her collaborators reproduced these structures and showed that they were a natural consequence of the solar magnetic field interacting with the slowing plasma in the heliosheath. The sun's magnetic field, which reverses polarity roughly every 11 years as part of the solar cycle, creates a corrugated sheet of current flowing outward through the heliosphere. When this corrugated sheet reaches the heliosheath and the flow slows and compresses, the corrugations fold and pinch off into bubbles. The result is a region that looks nothing like the smooth, streamlined pictures in older textbooks. The edge of the solar system was not an elegant boundary. It was a mess, a productive, scientifically extraordinary mess that revealed the heliosphere to be far more dynamic than anyone had drawn it. The flow of the solar wind in the heliosheath added another layer of surprise. Models predicted that the plasma would flow along the heliopause in a relatively orderly pattern, turning from radially outward to roughly tangential along the boundary. Voyager 2's plasma instrument measured the actual flow. It was not orderly. The flow direction changed unpredictably. In some measurements, the plasma appeared to have reverse direction, flowing back toward the sun rather than away from it. The heliosheath was full of eddies, reversals, and lateral motions that suggested the boundary region was being buffeted by forces from both inside and outside simultaneously. The reversals were not random noise, they had structure, they appeared in clusters, lasting weeks or months at a time, and they were correlated with changes in the magnetic field direction. Something in the heliosheath was pushing the solar wind backward in specific locations and at specific times. The most likely explanation was the pressure from the interstellar medium outside was not uniform. It varied across the face of the heliopause, creating regions where the outside pushed harder and regions where it eased off. The heliosheath was responding to those variations in real time, sloshing and churning in response to a force that the probes could not directly see but could measure through its effects on the plasma flowing around them. The boundary was not just a static structure being crossed. It was a living negotiation between two opposed pressures, each variable, each responsive to the other, and the heliosheath was the zone where that negotiation played out in physical terms. This was not failure to understand. This was the discovery of complexity that only direct measurement could reveal. The models were not wrong in their basic physics, and they were wrong in their assumptions about how simple the boundary would be. And they were wrong because no one had ever been there to check. Every prediction about the termination shock and the heliosheath had been made from the inside, inferred from remote measurements and theoretical extrapolation. The Voyager probes were the first direct witnesses. And witnesses have a way of making theories uncomfortable. While the boundary science unfolded, the engineering story continued in parallel. Every year that passed brought the power budget closer to a critical threshold. By the early 2000s, each spacecraft was generating roughly 60 to 70% of its original wattage. Instruments had been shut down progressively. On Voyager 1, the plasma science instrument was already gone. The ultraviolet spectrometer was turned off. The photopolarimeter had been switched off. On Voyager 2, the power situation was slightly better, but the same slow arithmetic of decay applied. The engineers at JPL developed strategies that bordered on the ingenious. They turned off heaters for instrument platforms and accepted that those platforms would cool to temperatures far below the design limits, hoping the hardware would survive conditions it was never tested for. In many cases, it did. In some cases, the hardware not only survived, but performed better cold than the engineers had any right to expect. Thruster systems that had been flagged as potentially unusable decades earlier were tested again and found still operational. Backup systems that no one had activated since the 1970s were brought online when primary systems degraded. Every component on the spacecraft was evaluated not for whether it was within its rated operating parameters, because almost nothing was anymore, but for whether it could be coaxed into functioning one more year in conditions its designers never imagined. The communication link itself required its own kind of survival. As the probes moved farther from Earth, the signal weakened. By the 2000s, the radio signal arriving from each spacecraft carried a power measured in fractions of a billionth of a watt. The Deep Space Network, the array of massive dish antennas spread across California, Spain, and Australia that NASA uses to communicate with distant spacecraft, had to devote its largest dishes and its most sensitive receivers to pull the Voyager signal out of the background noise of the universe. Scheduling time on those antennas became a negotiation in itself, because other missions also needed them. The Voyager team learned to work within narrow windows, prioritizing the data that mattered most. compressing what they could, and accepting gaps in coverage when higher priority missions took precedence. The low-energy charged particles instrument on Voyager 1 contained a stepper motor, a small mechanical device that rotated the instrument's detector in discrete steps to scan different directions. That motor had been tested on the ground to roughly 250,000 steps. By the time it was eventually shut down in 2026, it had completed more than 8.5 million steps and was still functioning. It continued to work even after its supplemental heater was turned off, and its temperature dropped to -62 degrees Celsius. The principal investigator for that instrument, Starmartios Cree Me Gis of the Johns Hopkins Applied Physics Laboratory, described it as the stuff that dreams are made of. These were not instruments designed for this. They were not rated for these temperatures, these distances, or these timescales. They survived because the engineers who built them in the 1970s had over-engineered them, probably without fully realizing how much margin they were building in. And they survived because the mission operations team at JPL treated every watt, every degree of temperature, and every byte of data as a resource too precious to waste. The long silence between the planets and the termination shock was not silence at all. It was preparation. The probes were aging. The power was declining. The instruments were being rationed, but the data continued flowing, and the slow, patient accumulation of measurements through the 1990s and early 2000s laid the groundwork for everything that followed. By the time Voyager 1 crossed the termination shock in 2004, it was 27 years old. By the time Voyager 2 crossed in 2007, it was 30 years old. Each spacecraft had already far exceeded its design lifetime by a factor of more than 6. And the most important boundary, the one that the entire Voyager Interstellar mission was designed to reach, was still ahead. The heliopause, the true outer edge of the sun's influence, the place where the solar wind stops entirely and the interstellar medium begins, the place where a spacecraft would, for the first time in human history, leave the bubble that the sun has blown around its family of planets and enter the space between the stars. The termination shock had been a revelation. The heliosheath was more complex than anyone imagined, but the heliopause was the prize, and reaching it would require crossing the full width of the heliosheath, a region whose thickness no one could predict with confidence because no one had ever measured it. Models suggested it might be 30 to 50 astronomical units thick. At the probe's speed, that translated to a decade or more of additional travel, another decade of power loss, another decade of instrument shutdowns, another decade of engineering decisions made in the dark across light hours of communication delay. The question was not whether the heliopause existed. The physics demanded it. The question was whether the probes would still be alive when they got there. And beyond that question lay an even deeper one that the termination shock had only begun to answer. What shape is the solar system? Not the shape of the planetary orbits, which astronomers had understood for centuries. The shape of the bubble, the heliosphere itself. Is it round? Is it elongated like a comet, with a long tail trailing behind as the sun moves through the interstellar medium? Is it something else entirely? Voyager 1 and Voyager 2 had crossed the termination shock at distances that differed by 10 astronomical units. That single data point already proved the boundary was asymmetric. But 2 points are not enough to draw a shape. The true geometry of the heliosphere remained unknown. It remains debated to this day. The termination shock was the first answer to a question that most people did not know was being asked. It proved that the solar system has a physical edge. Not a theoretical line on a chart, but a real, measurable, dynamic structure that you can fly through and come out the other side changed. The shock was not where the models said it would be. It was not symmetric. It did not behave the way textbooks predicted. And the region beyond it was wilder and more complex than anyone had drawn. But the shock was only the outer porch. The front door was still ahead. And what lay beyond that door was a region that no human machine had ever entered. A place that the sun does not control, where the magnetic field belongs to the galaxy, where the plasma was ejected by stars that died millions of years ago, and where the very concept of the solar system as a bounded, defined territory would be tested by the simplest possible experiment. Fly through the wall, see what is on the other side, report back. Both probes were still alive, both were still transmitting, and both were heading slowly, patiently, irreversibly toward the edge. The heliosheath was supposed to be a waiting room, a transition zone, thick but finite, between the termination shock and the true outer boundary, where the solar wind gives way to the interstellar medium entirely. Cross the shock, traverse the sheath, and eventually you reach the heliopause, the final wall, the place where inside becomes outside. What the Voyager probes found in the heliosheath was not a waiting room. It was a region with its own character, its own surprises, and its own capacity to overturn assumptions. But for all the complexity of the heliosheath, it was still the sun's territory. The plasma was still solar. The magnetic field was still rooted in the sun's rotation. The particles, however turbulent and tangled, were still products of the solar wind. Everything Voyager measured in the heliosheath, no matter how surprising, was still happening inside the bubble. The heliopause was different. The heliopause was the threshold between the sun's influence and everything else. Cross it and you're no longer inside the protective cocoon that the sun has maintained around its planets for roughly 4.5 billion years. The plasma surrounding you is no longer solar. The magnetic field threading through the gas no longer traces back to the sun's surface. You are immersed in material that was produced by other stars, some of them long dead, scattered into the interstellar void by supernova explosions millions of years ago. You are, for the first time, in the galaxy's own medium. That crossing was what the entire Voyager interstellar mission existed to reach. And for years, nobody knew when it would happen, or whether the instruments would still be functioning when it did. Voyager 1 pushed through the heliosheath for 8 years after crossing the termination shock. During those years, the data told a story of increasing strangeness. The magnetic field in the heliosheath grew more intense as the solar plasma piled up against the approaching boundary. The flow of the solar wind, already disrupted at the shock, became even more erratic. In some periods, the radial speed of the plasma measured by the particle instruments dropped to 0. The solar wind had literally stopped moving outward. It was being pressed back by the interstellar medium on the other side. The cosmic ray counts continued their long upward trend. Galactic cosmic rays, the high-energy particles that originate from beyond the solar system, were arriving in steadily increasing numbers. The heliosphere's ability to deflect them was weakening as the probe moved closer to its outer edge. Each increase in the cosmic ray count was a signal. The boundary was getting closer. Then, beginning in mid-2012, the data shifted dramatically. On July 28th, 2012, the galactic cosmic ray count on Voyager 1 spiked upward. Within days, it had increased by roughly 9%. At the same time, the count of lower energy particles originating from within the heliosphere dropped sharply. The probe appeared to have crossed into a new region. But then, within days, the readings reversed. The cosmic rays dropped back. The heliospheric particles returned. Voyager 1 had apparently crossed a boundary, then crossed back. This happened multiple times through late July and into August. The probe was skating along the edge, dipping in and out of a transition region as the boundary itself moved back and forth across the spacecraft's position. The heliopause was not a rigid surface. It was breathing, expanding and contracting in response to fluctuations in both the solar wind pressure from inside and the interstellar medium pressure from outside. Voyager 1 was caught in the oscillation, like a swimmer being pushed back and forth by waves at the edge of a shoreline. Then, on August 25th, 2012, the readings changed for the last time. The galactic cosmic ray intensity jumped to its highest sustained level. The heliospheric particle counts plummeted to near zero and stayed there. Whatever Voyager 1 had crossed into, it did not cross back out. But the confirmation was not immediate. And the reason for the delay reveals something important about how science actually works at the frontier. The most direct way to confirm a heliopause crossing would have been to measure the plasma density on both sides. If the probe had moved from the tenuous solar plasma to the denser interstellar plasma, the density should have increased dramatically. That measurement would have been straightforward for the plasma science instrument. But Voyager 1's plasma science instrument had been dead since 1980. There was no direct plasma density measurement available. The magnetic field data added confusion rather than clarity. Models predicted that when the spacecraft crossed the heliopause, the direction of the magnetic field should change. Inside the heliosphere, the field follows the spiral pattern imposed by the sun's rotation. Outside, it should align with the magnetic field of the local interstellar medium, which is oriented differently. Voyager 1's magnetometer showed that the field intensity changed at the boundary, but the direction did not shift as dramatically as expected. The field outside appeared to be roughly aligned with the field inside, which puzzled researchers and fueled months of debate about whether the crossing had truly occurred. The breakthrough came from an unexpected source. In April of 2013, more than 7 months after the suspected crossing, a coronal mass ejection, a massive burst of plasma and magnetic field erupted from the sun, arrived at Voyager 1's location. It had taken 13 months to travel from the sun to the spacecraft. When it hit the plasma surrounding Voyager 1, it made that plasma vibrate. The plasma wave subsystem, the instrument with 2 long antennas trailing behind the spacecraft, detected the vibrations. The oscillations rang at a specific frequency, and that frequency was directly related to the density of the plasma in which the spacecraft was immersed. The density was more than 40 times higher than anything measured in the heliosheath. 40 times. It was exactly the kind of density expected in the interstellar medium. The measurement was unambiguous. Voyager 1 was surrounded by interstellar plasma. Working backward from the plasma density measurement and the particle data, the science team pinpointed August 25th, 2012 as the date of the heliopause crossing. On that day, at a distance of approximately 122 astronomical units from the Sun, roughly 11.5 billion miles, Voyager 1 became the first human-made object to enter interstellar space. Ed Stone, who had served as the Voyager project scientist for more than 4 decades, said it plainly: "We made it. And we did it while we still had enough power to send back data from this new region of space." The announcement, when it was formally published in September of 2013, was received as one of the landmark achievements in the history of exploration. But within the scientific community, the excitement was tempered by an awareness of how much remained unknown. Voyager 1 had crossed the boundary. It had confirmed that the boundary exists. It had measured the density on the other side, but it had done so with incomplete instrumentation. The plasma science instrument was gone. The full picture of what the heliopause looks like, how the transition occurs in detail, and what the plasma conditions are on both sides remained only partially drawn. That is why Voyager 2's crossing, 6 years later, was in many ways even more important. Voyager 2 arrived at the heliopause on November 5th, 2018, at a distance of approximately 119 astronomical units from the Sun, roughly 3 astronomical units closer than its twin. The difference in crossing distances was itself significant. It confirmed again that the heliosphere is not spherical. The boundary sits at different distances in different directions, shaped by the pressure of the interstellar medium and the magnetic field geometry of both the solar and interstellar environments. But the real prize was the plasma science instrument. The instrument Voyager 1 had lost before it even left Saturn behind. On Voyager 2, it was still working. And it delivered. The instrument had been operating continuously since before launch. More than 41 years of unbroken data from a detector measuring the charged particles flowing around the spacecraft. When the other Voyager reached the heliopause without this tool, scientists could measure the density only indirectly, through plasma wave oscillations triggered by distant solar eruptions. They had to wait for the Sun to ring the interstellar medium on their behalf. Voyager 2 needed no such workaround. It could measure the plasma directly, in real time, sampling the density and speed and temperature of the charged particles flowing past its detector as the spacecraft moved through the boundary. For the first time, scientists had direct measurements of the plasma on both sides of the heliopause from the same spacecraft crossing the same boundary. The data showed that as Voyager 2 approached the heliopause from inside, the solar wind plasma slowed, heated, and grew denser. The plasma was piling up against the boundary like traffic approaching a bottleneck. Then, at the crossing itself, the solar plasma vanished. Within a single day, the instrument registered a steep drop in solar particles and a corresponding appearance of a new plasma population with different characteristics. The interstellar plasma was colder than the solar plasma in the heliosheath, but hotter than many models had predicted for the undisturbed interstellar medium. The temperature in the very local interstellar medium, measured by Voyager 2, was approximately 54,000 degrees Fahrenheit. That number sounds alarming. It is important to understand what temperature means in this context. The interstellar medium is extraordinarily thin. A cubic centimeter of this plasma contains, on average, roughly 1/10 of a particle. That is a vacuum far more extreme than anything achievable in a laboratory on Earth. When scientists say the temperature is 54,000 degrees, they mean the individual particles are moving at speeds corresponding to that thermal energy. but there are so few of them that you could pass your hand through this plasma and feel nothing. There is no heat in the way a human body would experience it. There is energy per particle, but almost no particles. The interstellar medium is blisteringly hot and utterly empty at the same time. The plasma science instrument also revealed something that no other measurement could have captured. A thin boundary layer, just on the outside of the heliopause, where the plasma appeared to be a mixture. Not purely solar, not purely interstellar. A blend of both, as if the two populations of charged particles were interpenetrating across the boundary at a microscopic level. The layer was narrow, and Voyager 2 crossed it quickly, but its existence confirmed what the particle data had been hinting at since the termination shock. The heliopause is not airtight. It leaks. Material from inside seeps out. Material from outside seeps in. The boundary is real, but it is porous, and the transition from one domain to the other happens not in a single clean step, but across a gradient that the plasma instrument could trace in detail. The magnetic field data from Voyager 2's crossing added another layer. Unlike Voyager 1, which saw little directional change in the field across the heliopause, Voyager 2 detected a modest rotation. The interstellar magnetic field was oriented somewhat differently from the solar field in the heliosheath, though the transition was not as dramatic as some models had predicted. The two crossings taken together suggested that the magnetic field configuration at the heliopause is complicated and variable, different at different locations, and probably influenced by the angle at which the solar and interstellar fields meet. 5 papers were published simultaneously in the journal Nature Astronomy in November of 2019, 1 year after the crossing, each analysing a different aspect of Voyager 2's heliopause passage. One paper focused on the plasma measurements, another examined the magnetic field transition, a third analysed the cosmic ray data, a fourth studied the low-energy particle populations, and a fifth attempted to synthesize all the data into a coherent picture of what the heliopause actually is. Together, they represented the most detailed portrait ever assembled of the boundary between the Sun's domain and the galaxy beyond. And together, they confirmed something that the science team had suspected for years. The heliopause is not a wall. It is not a clean separation. It is a leaky, dynamic, living boundary through which material and energy pass in both directions. Solar material leaks outward. Interstellar material leaks inward. The boundary responds to changes in the solar wind, adjusting its position and character on timescales of months and years. It breathes with the solar cycle. It flexes when the sun erupts. It's a boundary in the same sense that a coastline is a boundary between land and sea. The edge is real, but it is never the same twice. With both probes now beyond the heliopause, a new chapter of discovery opened. One that almost no one had anticipated in detail, because no one had ever had instruments in interstellar space before. The first ongoing discovery was about the density of the very local interstellar medium itself. Before the heliopause crossings, the only way to estimate the interstellar density near the solar system was through indirect methods, ultraviolet observations, remote sensing of scattered solar photons, and theoretical models. Voyager 1's plasma wave subsystem changed that. It could detect oscillations in the surrounding plasma, and the frequency of those oscillations revealed the electron density directly. The initial density measurements came from what scientists call plasma oscillation events. When a shockwave from a coronal mass ejection reached Voyager 1's location in interstellar space, it compressed the local plasma and triggered ringing at the plasma frequency. By measuring that frequency, researchers could calculate the density. The problem was that these events were rare. They depended on the sun erupting with enough force to send a pressure wave all the way through the heliosphere and into interstellar space. It happened perhaps once a year. The density map was sparse, a few data points scattered across years. Then, in 2017, something new appeared in the plasma wave data. Stella Koch-Ocker, a graduate student at Cornell University working with the Voyager plasma wave team, discovered a faint, persistent narrowband signal in the data that had not been identified before. It was not the dramatic ringing triggered by solar shockwaves. It was quieter, steadier, a continuous hum sitting just above the noise floor of the instrument. Finding it was not straightforward. The plasma wave subsystem was designed in the early 1970s to detect much stronger signals. Its sensitivity was extraordinary for its era, but the instrument was never intended to listen for the thermal whisper of undisturbed interstellar electrons. The signal Ocker found was faint enough that it sat in the margin between real detection and instrument noise. Distinguishing it required careful analysis of the frequency spectra over years of accumulated data, separating the persistent narrowband tone from the occasional louder plasma oscillation events and from the instrument's own electronic hum. The supply power line at 2.4 kHz had to be masked out. Background noise had to be equalized across observing sessions. What remained, once the artifacts were stripped away, was a thin, steady line in the frequency data. It was always there. It had been there since at least 2017, and it tracked the plasma density. This persistent emission, which Ocker described in a paper published in Nature Astronomy in 2021, gave Voyager 1 the ability to measure the interstellar plasma density continuously, rather than waiting for occasional solar eruptions to ring the local environment. The signal appeared to be produced by the natural thermal motions of the electrons in the interstellar plasma, a kind of background murmur that the extremely sensitive plasma wave antennas could just barely detect. The significance of this discovery is difficult to overstate. Before Ocker's finding, the density profile of the very local interstellar medium was a connect-the-dots sketch, a handful of points spaced years apart, each triggered by a solar eruption whose timing was unpredictable. After her finding, the sketch became a continuous line. For the first time, scientists could watch the density of the interstellar medium change in real time as the spacecraft moved through it. Not once a year. Continuously. The interstellar medium had gained a pulse, and Voyager 1 could feel it. With this signal, the team constructed the first continuously sampled density profile of the very local interstellar medium. The picture that emerged was not smooth. The density fluctuated on scales of a few astronomical units, showing structures and variations that were consistent with interstellar turbulence. The medium between the stars was not a uniform bath. It had texture. It had variations in density on scales that the spacecraft could cross in months or years. It was, in its own subtle way, as structured and complex as the heliosheath had been, just quieter and operating on different physical principles. Then came the anomaly that nobody anticipated. In 2020, Voyager 1's magnetometer registered an abrupt jump in the intensity of the magnetic field embedded in the interstellar plasma. Simultaneously, the plasma density measurements from the plasma wave subsystem showed a corresponding increase. This was not unheard of. Similar jumps had been detected before and had returned to baseline within months. Scientists attributed those earlier events to pressure fronts, waves generated when solar eruptions pushed outward against the heliopause and sent reverberations rippling through the interstellar medium beyond. The sun was acting like a piston, compressing the surrounding environment in pulses. But the 2020 anomaly did not return to baseline. The elevated magnetic field intensity and increased plasma density persisted. Months passed. The readings did not relax. This persistence was what set the anomaly apart from everything that came before. A solar pressure wave should dissipate. It should travel outward, compress the medium, then pass, leaving the readings to return to their prior values. That was the pattern from every previous event. The 2020 readings broke the pattern. They rose and stayed. 6 months, a year. The instruments kept reporting the same elevated values as if Voyager 1 had moved into a fundamentally different region of space and was not coming back out. Then, in November of 2023, a corrupted memory chip in Voyager 1's flight data subsystem rendered all transmissions unintelligible. The spacecraft went effectively silent, unable to package its science data into a form that Earth could read. For 6 months, the mystery sat unresolved while engineers at JPL worked one of the most extraordinary remote repairs in the history of technology, diagnosing a single failed chip aboard a spacecraft more than 15 billion miles away, rewriting the affected code into fragments, scattering those fragments into unused corners of a computer with roughly 69 kilobytes of total memory, and uploading the fix through a communication link so slow that each command took nearly a full day to arrive. In May of 2024, Voyager 1 resumed transmitting science data. The magnetometer and the plasma wave subsystem came back online, and the readings were still elevated. That was the moment the conversation in the heliophysics community changed. 6 months of silence, then the data returns, and the anomaly is still there. Whatever caused it, it was not a transient event. It was not a wave passing through. It was either a region of space with genuinely different properties that the spacecraft had entered and was still inside, or it was a sustained change in the conditions of the medium itself. Archdam Esakbo, an astrophysicist at NASA's Goddard Space Flight Center and principal investigator for the magnetometer, proposed a hypothesis that reshaped the conversation. He suggested that Voyager 1 may have entered a small cloud of ancient interstellar plasma carrying its own magnetic field, one imprinted by whatever star or star-forming region originally ejected it into the void. If true, the probe was no longer just measuring the general interstellar medium. It was sampling a specific parcel of material with its own history, its own origin, its own magnetic signature distinct from the background. The interstellar medium in this picture is not a homogeneous sea. It is a patchwork of parcels, each carrying the fingerprint of the astrophysical event that created it. Some parcels may be remnants of supernova explosions. Others may have been blown off the surfaces of aging red giant stars. Each one drifts through the galaxy, mixing slowly with its neighbors, but retaining its individual characteristics for millions of years. Voyager 1 might have crossed from one parcel into another. Other scientists offered competing explanations. Some believed the readings were still consistent with a particularly large and sustained solar pressure wave, one generated by an especially powerful sequence of coronal mass ejections during the recent solar maximum. In this view, the elevated readings are still solar in origin, just bigger and longer lasting than previous events. The sun's fingerprints, not of foreign clouds. Others questioned whether Voyager 1 had ever fully exited the heliosphere at all, suggesting that the elevated readings might reflect a boundary layer more complex than previously mapped. A region where the heliospheric and interstellar magnetic fields intermingle in ways that none of the crossing models had captured. In this picture, the heliopause is not a surface that you cross once and leave behind. It is a thick, messy region that extends further outward than anyone realized, and Voyager 1 might still be partially inside it. The debate is ongoing. As of 2026, no single explanation has been confirmed. Each hypothesis makes different predictions about what the instruments should see as Voyager 1 moves farther outward. If it is a cloud, the anomaly should eventually end as the probe exits the other side. If it is a sustained solar pressure wave, the readings should gradually decay. If it is an extended boundary layer, the transition to undisturbed interstellar conditions should be more gradual and complex than any model currently describes. The data continues to arrive. The answer may take years, but the very existence of this debate illustrates something profound about what the post-planet Voyager mission has become. The probes are not simply confirming theoretical predictions. They are generating new questions that the theory had never considered. The interstellar medium was supposed to be the background, the quiet stage on which the heliosphere performs. Instead, it has its own drama, its own complexity, and its own ability to surprise. While the probes push deeper into interstellar space, a parallel scientific effort was building back at Earth. The question of the heliosphere's shape, first raised by the asymmetry of the termination shock crossings, had become one of the most contested topics in heliophysics. For decades, the standard picture showed the heliosphere shaped like a comet, a rounded nose pointing in the direction the solar system is moving through the interstellar medium, and a long tail stretching behind it, swept back by the flow of the interstellar wind. It was an intuitive shape. It made physical sense, and it appeared in virtually every artist's rendering and textbook diagram for half a century. In 2015, Meh Rajiv Ophir, a professor of astronomy at Boston University, and her collaborator James Drake of the University of Maryland, published research that challenged this picture fundamentally. Using computer simulations that treated the solar wind's components separately, particularly the pickup ions that carry so much of the energy in the outer heliosphere, they found that the heliosphere might not have a long tail at all. Their model produced a shape that the team described as a deflated croissant, a bulbous central region with two jets of material curling away on either side, far more compact and rounder than the classic comet picture. The reaction was fierce. Conferences became contentious. The comet model had decades of momentum behind it, but O.H. Fur's model was grounded in physics that the older models had simplified or ignored. The pickup ions, the same particles that had dominated the energy budget at the termination shock, played a different role in the sheath and at the heliopause. When their pressure was accounted for properly, the tail collapsed. The heliosphere became more spherical, and the elongated comet shape vanished from the simulations. Then, in 2017, data from the Cassini spacecraft, which had been orbiting Saturn, added another twist. by timing energetic neutral atoms that had bounced off the heliopause boundary and streamed back toward the inner solar system. Cassini scientists concluded that the heliosphere might be very nearly round. Not a comet, not a croissant, a sphere. The result was published with fanfare and immediately disputed. Tom Crimagis, who had led experiments on both Cassini and Voyager, acknowledged that the finding was difficult to accept. The community was not ready for a spherical heliosphere. It contradicted too many established ideas. As of 2026, the debate is not settled. O.H. Furr's group has continued refining their models, producing shapes that split the difference between a croissant and a sphere. Other teams have argued for intermediate geometries. The two Voyager crossings provide constraints, but only at 2 points. 2 points cannot define a three-dimensional shape. The heliosphere could be almost any geometry that passes through those two measured positions, and the range of possibilities remains wide. This is precisely why NASA launched the Interstellar Mapping and Acceleration Probe in September of 2025. IMAP, as the mission is known, is now in orbit at Lagrange Point 1, roughly 1 million miles from Earth, where it began its primary science mission in February of 2026. The probe carries 10 instruments designed to map the energetic particles and neutral atoms streaming back from the heliosphere's boundaries. Where the Voyager probes provide point measurements, biopsies of the boundary at two specific locations, IMAP will attempt to construct a global picture, a full map of the heliosphere's shape, drawn from particles that have interacted with the boundary and travelled back inward. David McComas, the principal investigator for IMAP and a professor of astrophysical sciences at Princeton University, has described the Voyager measurements as essential but fundamentally limited. The Voyagers are very much like biopsies of the heliosphere, he has said. We know nothing about the global three-dimensional structure of the outer heliosphere from just these two sets of points. IMAP is designed to fill in the blanks. Its measurements, combined with the ongoing data from both Voyager probes, will for the first time allow scientists to construct a comprehensive model of the structure that surrounds and protects the entire solar system. The shape of the heliosphere is not an abstract geometric puzzle. It determines how much galactic cosmic radiation reaches the planets. It affects the space weather environment that astronauts and satellites must endure. It defines the boundary conditions for any future spacecraft that might one day attempt to leave the solar system and travel to another star. And the heliosphere's shape is not fixed. It changes with the solar cycle. It responds to the interstellar environment through which the solar system is currently moving. The Sun orbits the center of the Milky Way, and as it does, it passes through different regions of the interstellar medium with different densities, different temperatures, and different magnetic field strengths. The heliosphere has been one shape during human history. It was a different shape a million years ago. It will be a different shape a million years from now. The bubble is a living structure, born from the interaction between one specific star and the specific patch of galaxy it happens to be traveling through. The Voyager probes revealed this, not in a single moment of discovery, but across decades of patient measurement, each year adding another data point, each crossing refining the picture, each anomaly opening a new question. The termination shock was not where models predicted. The heliosheath was not smooth. The heliopause was not clean. The interstellar medium was not uniform. and the shape of the entire structure remains genuinely unknown. Every one of these findings came after the planets were gone. Every one of them required that the probe survive far beyond their intended lifetime. Every one of them depended on instruments designed in the early 1970s, continuing to function in an environment they were never built to encounter. And every one of them expanded the human understanding of what the solar system actually is. Not just a collection of worlds orbiting a star, but a structured, bounded, dynamic territory embedded in a larger medium that presses against it from all sides. The edge of the solar system is not empty. It is not a clean line. It is not a gradual fade. It is a region of extraordinary complexity, revealed one measurement at a time by two machines that refuse to die. And as both probes continue outward, deeper into the very local interstellar medium, the instruments that remain are still recording, still listening, still detecting the faint hum of the plasma between the stars. The data is still arriving at Earth, traveling at the speed of light, taking more than 22 hours for each signal to cross the distance. The transmitter power on each spacecraft is roughly the wattage of a refrigerator light bulb. The signal that reaches the deep space network antennas on Earth is so faint that the total energy collected from Voyager 1 over the entire course of the mission would not be enough to light a snowflake falling in a dark room. And yet, it is enough. The antennas hear it. The data is decoded. The numbers are sent to the science teams. And the picture of the interstellar medium grows a little clearer with each passing month. But the probes are dying. The power is fading. The instruments are being sacrificed one by one. And what that final decline means, not just for the spacecraft, but for what they taught humanity about the space beyond the last world, is the story that remains to be told. On February 27th, 2026, during a routine roll maneuver, Voyager 1's power levels dropped unexpectedly. The drop was small, a few watts. On any spacecraft closer to home, with any margin to spare, it would have been a footnote in an engineering log. On Voyager 1, nearly 16 billion miles from Earth, running on a power supply that had been losing 4 watts per year for almost half a century, it was a crisis. The mission engineers at JPL knew what would happen if the power fell further. The spacecraft's undervoltage fault protection system would activate automatically, shutting down components on its own in an uncontrolled sequence designed to protect the probe from electrical damage. Recovery from an autonomous shutdown at that distance, across a communication link that takes more than 22 hours each way, would be agonizing. Weeks of careful work, with no guarantee of success. They had been through something like it before, during the 2023 memory chip failure, and the experience had sharpened their awareness of how thin the margins had become. The decision was made to shut down the low-energy charged particles instrument. The same instrument whose stepper motor had exceeded its design life by a factor of 34. The same instrument that had been measuring ions, electrons, and cosmic rays since before either probe left Earth. The command was sent on April 17th, 2026. It arrived at Voyager 1 roughly 23 hours later. 3 hours and 1 minute after that, the instrument went dark. Kareem Badarudin, the Voyager mission manager at JPL, put it simply. While shutting down a science instrument is not anybody's preference, it is the best option available. With the low-energy charged particles instrument gone, Voyager 1 now operates with 2 functioning science instruments, the magnetometer and the plasma wave subsystem. Two instruments built in the early 1970s, flying through interstellar space, powered by the heat of decaying plutonium, returning data on a transmitter that radiates roughly 23 watts, less than the power of a dim household bulb. Voyager 2 still carries 3 working instruments. Its plasma science instrument, the one that died on Voyager 1 in 1980, is still returning data after nearly 49 years. The loss of each instrument narrows the window through which humanity can see interstellar space. Every shutdown removes a dimension from the picture. The low-energy charged particles instrument was the only tool on Voyager 1 that directly measured the population of particles at the energies most relevant to understanding the structure of the local interstellar medium. Without it, the magnetometer can still feel the field, and the plasma wave subsystem can still listen for density oscillations, but the full particle environment is now invisible from Voyager 1's vantage point. The measurement is gone. The medium has not changed. Only our ability to perceive it has diminished. This is the condition of the mission in 2026. 2 spacecraft, both beyond the heliopause, both in interstellar space, both still transmitting, both slowly going blind, and yet the engineering team is not surrendering. They are preparing what they have informally named the Big Bang. It is not an explosion. It is a coordinated swap. The plan is to shut off several powered devices on each spacecraft simultaneously, primarily heaters that keep the thruster fuel lines from freezing, and replace them with alternative devices that accomplish the same warming function at lower total power consumption. The name comes from the all-at-once nature of the change. Rather than making incremental adjustments over months, the team will flip the configuration in a single commanded sequence. The stakes are severe. If the fuel lines freeze, the thrusters that keep the spacecraft's antenna pointed at Earth become inoperable. If the antenna drifts off target, the data link is lost. Recovery from a lost antenna lock at interstellar distances may be impossible. The Big Bang is being tested on Voyager 2 first, during May and June of 2026, because Voyager 2 has slightly more power remaining and is closer to Earth, making it the safer test subject. If the tests succeed, Voyager 1 will undergo the same procedure no sooner than July. If it works, the power savings could buy both probes an additional year or more of science operations. There is even a possibility, slim but real, that saved power could allow one or more shut-down instruments to be reactivated. The engineers are not promising that. They are working toward it. This is what the Voyager mission looks like now. Not the gleaming hardware of a 1977 launch. Not the triumphant press conferences of the Jupiter and Saturn encounters. Not the poetry of the pale blue dot. It looks like a small team of engineers in a building in Pasadena, California, managing a power budget measured in single-digit watts, sending commands to machines older than most of the people in the room, waiting a full day for each round-trip communication, and fighting for every additional month of data from the only instruments humanity has ever placed beyond the sun's influence. It is not glamorous. It is essential. In November of 2026, Voyager 1 will reach a milestone that has no scientific significance, but carries symbolic weight that is difficult to dismiss. The spacecraft will be one light day from Earth, 16 billion miles, the distance at which a signal traveling at the ultimate speed limit of the universe, the speed of light itself, takes 24 hours to make the journey. A command sent on a Monday morning will not arrive until Tuesday morning. The reply will not return until Wednesday, one light day. The phrase sounds almost modest against the backdrop of a galaxy that spans 100,000 light years. But it is a distance that no human-made object has ever reached before. It is farther than any tool, any instrument, any extension of human reach has ever traveled from the place where it was built, and it is still, by interstellar standards, virtually nowhere. Voyager 1 will not reach the inner edge of the Oort cloud, the vast spherical shell of icy bodies that marks the outermost gravitational boundary of the solar system, for approximately 300 years. It will not pass near another star for roughly 40,000 years, when it drifts within about 1.6 light years of a small star in the constellation Camelopardalis, catalogued as AC plus 793888. Voyager 2, on a different trajectory, will pass within roughly 1.7 light years of the red dwarf Ross 248 in approximately 40,000 years as well. These numbers reveal something that the story told so far makes easy to overlook. The Voyager probes crossed the heliopause. They left the sun's plasma bubble. They entered interstellar space. But they have not left the solar system. Not even close. The Oort cloud, a roughly spherical swarm of trillions of icy bodies loosely bound by the sun's gravity, extends from perhaps 2,000 astronomical units to as far as 100,000 astronomical units from the sun. The heliopause, where Voyager 1 crossed, sits at roughly 122 astronomical units. That is barely past the inner threshold of the Oort cloud's sparse beginnings, and nowhere near its outer edge. By gravitational reckoning, the probes are still deep inside the sun's domain. They will remain inside it for tens of thousands of years. This distinction matters because it reveals that the solar system has more than one edge, and the edges are not the same kind of thing. The Oort cloud boundary is gravitational. It marks the distance at which the sun's gravity can no longer hold objects in orbit. It is real, but it is passive. It does not do anything. It does not protect the planets from radiation. It does not interact with the interstellar medium. It does not change shape with the solar cycle. It is simply the farthest reach of the sun's gravitational pull. A line in the ledger of orbital mechanics. The heliosphere boundary is different in every respect. It is not gravitational. It is electromagnetic and fluid dynamic. It is the place where the sun's wind meets the galaxy's medium. It is active, it responds, it breathes, it shapes the radiation environment that every planet inside it experiences. It determines how many galactic cosmic rays reach Earth's atmosphere. It interacts with the interstellar medium in a two-way exchange of particles, fields, and pressure. It is, in the most literal sense, the edge that matters for life. Voyager found that edge, not the passive gravitational perimeter that will take 300 years to reach and 30,000 more to cross, but the active, dynamic, consequential boundary that defines the conditions under which the planets exist. The heliosphere is not the farthest edge of the solar system. It is the most important one, and it was invisible until 2 spacecraft carried instruments through it and reported what they felt. These numbers place the Voyager mission in the temporal context that the human mind struggles to hold. 300 years to the Oort cloud. 40,000 years to the nearest stellar approach. The probes will be dead and silent for almost all of that journey. The plutonium will have decayed below the threshold of usefulness within the next decade. The instruments will go dark one by one. The transmitters will fall silent. And the two spacecraft, inert and unresponsive, will continue outward on their trajectories, carrying their golden records and their dead instruments and the fading residue of human intention through a medium that does not care whether they are there. That image feels like an ending. It is not. Or rather, it is an ending only if you believe the probes were the point. They were not. The probes were the method. What they revealed is the point. And what they revealed didn't stop mattering when the cameras turned off or when the last instrument goes dark. What the Voyager probes revealed after the planets were gone is that the solar system has a structure beyond the planets. That structure is not empty space. It is not a gradual fade from something to nothing. It is a series of boundaries, each with its own physics, its own surprises, its own capacity to overturn decades of theoretical prediction. The termination shock, the heliosheath, the heliopause, the very local interstellar medium. Each of these regions was, before Voyager, a theoretical construct. A set of equations on a chalkboard. A chapter in a graduate textbook that began with the phrase, "It is expected that," and ended with assumptions that had never been tested. Voyager tested them, and the results were not what anyone expected. The termination shock was not where the models placed it. It was asymmetric by 10 astronomical units between the two crossing points. It transferred energy to interstellar pickup ions rather than to the solar wind itself. It did not accelerate anomalous cosmic rays at the locations where the probes crossed. The heliosheath was not a smooth transition zone, but a turbulent froth of magnetic bubbles and reversed flows. The heliopause was not a rigid wall, but a breathing, oscillating membrane that moved back and forth across Voyager 1's position multiple times before the final crossing. The interstellar medium beyond was not uniform, but textured with density fluctuations, turbulence, and possibly discrete clouds of plasma carrying magnetic signatures from ancient stellar sources. None of this was known before the probes arrived. None of it could have been known. Remote observation from Earth can infer the existence of the heliosphere. It can model the expected structure. It can detect the energetic neutral atoms that bounce off the boundary and stream back inward. But it cannot measure what the boundary feels like from the inside. It cannot record the moment of crossing. It cannot sample the medium on the other side and report its density, its temperature, its magnetic field strength, its turbulent spectrum. Only a probe can do that. Only a machine that is physically there, embedded in the environment, carrying instruments that interact with the particles and fields surrounding it, can provide the ground truth that transforms a theory into a measurement. The Voyager probes provided that ground truth, and they provided it only because they survived long enough to reach the boundaries. The survival was not inevitable. It was the product of conservative engineering in the 1970s, creative power management in the 1990s and 2000s, and a sustained institutional commitment to keep the mission funded and staffed for decades after the cameras stopped returning pictures. Every year that the probes operated beyond their design life was a year that could have been their last. And every year they survived brought them closer to a boundary that made the survival worthwhile. This is the deeper lesson of the Voyager interstellar mission. It is not simply that the probes kept going. Keeping going is what unpowered objects in space do by default. They drift. Persistence in a vacuum is free. What is not free is the ability to perceive. The instruments cost power. The data link cost power. The engineering team costs funding. The commitment to continue measuring, continue listening, continue decoding the faint signals from a spacecraft that most of the world had forgotten. That cost something that cannot be measured in watts or dollars. It cost attention. It cost patience. And it cost the willingness to believe that the most important discoveries might come not in the first 4 years of a mission, but in the 4th decade. The planetary encounters were spectacular. They rewired the public understanding of what the outer solar system contains. They gave humanity its first close look at the storms of Jupiter, the rings of Saturn, the strangeness of Uranus, the winds of Neptune, and the frozen geysers of Triton. Those encounters deserved their fame, but they were the opening act of a story that the public treated as the finale. The post-planet phase of the Voyager mission is the conceptual heart of the entire enterprise. It is the phase where the mission stopped visiting destinations and started revealing boundaries. It is the phase where the probes stopped being tourists and started being explorers in the truest sense, moving into territory that had no prior description, carrying instruments that could barely function, measuring an environment that no theory had accurately predicted. The termination shock was not a landmark anyone could point to on a map before Voyager arrived. The heliosheath was not a named territory in public consciousness. The heliopause was a theoretical line. The very local interstellar medium was a concept, not a place. Voyager made them real. And in making them real, the probes did something that the planetary encounters, for all their brilliance, could not do. They expanded the human map. The planetary encounters added detail to a map that already existed. Jupiter was on the map before Voyager arrived. Saturn was on the map. Uranus and Neptune were known objects whose positions and orbits had been calculated for centuries. What Voyager did at those worlds was fill in the details, replace the blurred outlines with high-resolution portraits. That is magnificent work, but it is work within a known framework. The map already had borders. Voyager coloured in what was inside them. The post-planet mission did something different. It extended the map itself. Before Voyager reached the termination shock, the edge of the solar system was a concept that existed primarily in equations. After the crossings, it was a measured feature with known properties at specific locations. Before Voyager crossed the heliopause, interstellar space was a theoretical region inferred from stellar observations. After the crossings, it was a place that contained a specific plasma density, a specific magnetic field, a specific temperature, all measured directly. The map did not get more detailed. It got larger. The boundary of what is known moved outward. That expansion is the Voyager mission's deepest legacy, not the photographs, not the golden records, not the cultural moment of the pale blue dot. Those are important. They are meaningful. They earned their place in the human story. But the expansion of the known, the pushing of the boundary between measured and unmeasured, between confirmed and conjectured, that is the thing that changes the scientific enterprise permanently. And the expansion is not finished. Both probes are still transmitting. The magnetometer on Voyager 1 is still detecting the interstellar magnetic field. The plasma wave subsystem is still listening for the hum of interstellar plasma. The data is still arriving, and the probes are still moving deeper into a medium that has never been sampled before at their current distances. Every mile they travel is a mile that extends the reach of direct human measurement. Not inference, not modeling, measurement. The interstellar medium is not the same everywhere. The Voyagers are currently traveling through a region known as the local interstellar cloud, a patch of partially ionized gas roughly 30 light-years across that the solar system entered somewhere between tens of thousands and hundreds of thousands of years ago. The Sun is near the edge of this cloud. Ahead, in the direction of Alpha Centauri, lies a different cloud with different properties. The interstellar medium is patchy, varied, and structured on scales that matter for the long-term evolution of the heliosphere. As the solar system orbits the galaxy and moves through different interstellar environments, the heliosphere changes shape. The boundary moves in and out. The shielding against galactic cosmic rays strengthens and weakens. The conditions that the planets experience, the radiation environment, the influx of interstellar dust, the pressure on the magnetic bubble, all of these change on timescales of thousands to millions of years. The heliosphere that protected Earth during the age of dinosaurs was not the same heliosphere that protects it now. And the heliosphere that will surround the solar system a million years from now will be shaped by whatever interstellar environment the Sun has drifted into by then. This is not abstract cosmology. It connects to questions about the history of life on Earth, the frequency of mass extinction events, and the long-term habitability of planets in general. A heliosphere that shrinks because the solar system enters a denser region of interstellar gas lets more galactic cosmic rays through to the inner planets. More cosmic rays means more radiation reaching the surface. More radiation affects biology. The connection is real and has been studied in the geological record, where episodes of elevated cosmic ray flux have been tentatively correlated with environmental changes on Earth. The evidence comes from multiple independent sources. Certain isotopes, such as beryllium-10 and carbon-14, are produced in Earth's atmosphere when galactic cosmic rays collide with nitrogen and oxygen atoms. These isotopes are preserved in ice cores, ocean sediments, and tree rings, creating a physical record of cosmic ray intensity stretching back hundreds of thousands of years. When researchers plot that record against the geological timeline, patterns emerge. Periods of elevated cosmic ray production appear to correlate, loosely but persistently, with periods of climate change, increased cloud formation, and in some analyses, with the timing of ice ages. The mechanisms are debated. One hypothesis holds that cosmic rays promote the formation of aerosol particles in the lower atmosphere, which seed cloud formation, which increases the planet's reflectivity, which cools the surface. The physics is plausible. The correlation is suggestive, but the chain of causation remains unconfirmed. What is less debated is the broader point. The heliosphere is not a permanent fixture. Its strength varies, its shape changes, and those changes have consequences that reach all the way to the surface of the planet you are standing on. Those constraints, sparse as they are, reach further than Earth's climate record. They extend to every star system in the galaxy. The implications extend beyond Earth. Every star in the galaxy is embedded in some version of the same relationship. Every star blows a wind. Every wind carves a bubble. Every bubble has a boundary, and every planet orbiting inside that bubble experiences a radiation environment that depends on the size, shape, and strength of the boundary between inside and outside. When astronomers assess the habitability of exoplanets orbiting other stars, the properties of the host star's astrosphere, its version of our heliosphere, are part of the calculation. A red dwarf with a weak wind might carve a small, thin bubble that lets most galactic cosmic rays through to any planet orbiting inside it. A young, active star might blow a heliosphere so large and dense that its planets are shielded far more effectively than Earth. The range of possibilities is enormous, and the models that estimate these astrospheres need at least one real-world example to anchor their predictions. That example is ours, and the only empirical data for what an astrosphere's boundary actually looks like, how thick the sheath is, how the shock behaves, how the heliopause leaks, comes from the Voyager probe's measurements of our own. 2 data points from 2 trajectories through one star's bubble. It is not much, but before 1977, it was nothing. IMAP, now beginning its science operations at Lagrange Point 1, will extend this work by constructing the global picture that the Voyager point measurements cannot provide. The 2 approaches are complementary. IMAP sees the whole boundary from the inside, painting a map in reflected particles. Voyager sees the boundary from the outside, reporting what it feels like to be immersed in the medium beyond. Together, they will give humanity its most complete picture of the structure that separates the solar system from the rest of the galaxy. And then, eventually the Voyager signals will stop. The plutonium will decay below the level needed to power even a single instrument. The transmitters will go silent. The antennas will stop broadcasting. The 2 spacecraft, one at roughly 38,000 and the other at roughly 34,000 miles per hour, will continue outward on their trajectories, gradually slowing under the faint gravitational influence of the Sun, but never stopping, never turning back. They will coast through the very local interstellar medium, through whatever clouds and structures lie ahead, carrying their dead instruments and their golden records through a silence that will last longer than human civilization has existed. In 40,000 years, when Voyager 1 passes near a star it will never see, and Voyager 2 glides past another, no signal will announce their arrival. No camera will photograph the approach. No magnetometer will measure the stellar wind of a foreign sun. The probes will be artifacts, fossils of a species that reach just far enough beyond its own neighborhood to learn that the neighborhood had an edge. But the knowledge they gathered will remain. Not on the spacecraft, not on the golden records, which were designed for a different purpose and a different audience. The knowledge lives in the data, archived on Earth, interpreted and reinterpreted by successive generations of scientists. The density of the interstellar medium at 122 astronomical units. The magnetic field direction at the heliopause. The temperature of the plasma between the stars. The turbulent spectrum of the very local interstellar medium. These numbers do not expire. They do not degrade with distance. They are the permanent yield of a mission that lasted decades longer than it was supposed to, and, in doing so, rewrote the map of everything. The Voyager probes were designed to visit planets. They did, and they were magnificent at it. But the planets were the part of the mission that the public could see and the textbooks could celebrate. The post-planet phase, the decades of quiet measurement in regions with no name and no camera-ready surface, was the part that changed what the solar system means. Before Voyager, the solar system was a set of worlds orbiting a star. After Voyager, the solar system is a bubble, a structured, bounded, dynamic, breathing structure carved out of the interstellar medium by the solar wind, wrapped in a termination shock, layered with a turbulent sheath, sealed by a heliopause, and embedded in a medium that has its own density, its own field, its own turbulence, and its own history. The planets orbit inside this bubble. They are the most visible features of the solar system, but they are not the whole story. They are not even the whole structure. They are contents, not container. The container was invisible until Voyager touched it. The container was theoretical until instruments that were never designed for the task measured its properties from the inside and then from the outside. The container is what defines the solar system as a physical territory in the galaxy, and its discovery belongs to two machines that were supposed to stop mattering after Saturn. There is something in this that goes beyond science. It is the recognition that the most important questions are often the ones that lie just past the boundary of what seems worth asking. The planets were the obvious targets. They were visible. They were beautiful. They drew funding, public attention, and scientific ambition. The space beyond the planets was not visible. It was not beautiful in any way that a camera could capture. It drew patience, endurance, and the quiet conviction that the unknown is worth measuring, even when no one is watching. The Voyager probes did not just cross the edge of the solar system. They revealed that the edge exists. They showed that the solar system does not trail off into nothing. It transitions. It changes state. It passes through boundaries that are physical, measurable, and consequential for everything inside them. And that transition, that passage from the sun's domain into the galaxy's own medium, is not an epilogue to the planetary story. It is the discovery that gives the planetary story its context. The planets orbit inside a bubble. The Voyager probes told us what the bubble is made of, where it ends, and what lies outside. That is not a footnote to the grand tour. It is the frame that holds the picture. Right now, in the middle of 2026, two spacecraft are falling deeper into interstellar space. Their instruments are fading. Their power is measured in watts that would not run a kitchen appliance. Their signals take nearly a full day to reach the antennas that listen for them. And those antennas are still listening. The engineers are still sending commands, the scientists are still reading the data, and the interstellar medium is still being measured for the first time at distances no human instrument has ever reached. Every day that the probes continue transmitting, the map gets a fraction larger. Every measurement extends the reach of direct human knowledge a little farther into the galaxy. And every watt of power spent keeping an instrument alive buys another data point in a record that will outlast the spacecraft, the mission team, and perhaps the civilization that built them. The Voyager probes were sent to the planets. The planets gave them speed. The speed carried them to the edge. And the edge turned out to be the most important thing they ever found. Not because it was beautiful, not because it made headlines, but because it was real. It was there. It had properties that no one had measured, and measuring it expanded the boundary of what humanity knows about the place it lives. The solar system does not end where the planets stop. It ends where the sun's wind meets the galaxy's breath. And the only reason we know that is because two small machines, built to last 4 years, carried a handful of instruments past the last familiar world and kept going until the instruments found something no one had ever touched. That is what the Voyager probes revealed after the planets were gone. Not that space continues, not that the mission kept running, but that the place where the planets end is where the solar system truly begins to show what it is. A territory defined not by its worlds, but by its boundary. a structure made visible only by crossing it, a map that gets larger only when someone is willing to keep walking after the landmarks disappear. The probes are still walking, the data is still arriving, and the edge of everything we know is still, right now, one day's light away and moving farther with every passing hour.